If you're deploying massive AI models in busy production environments, well, you already know that speed is literally everything. Welcome to this explainer on DeepSeek's new DSpark framework. Today, when diving deep into a truly brilliant serving optimization that dramatically speeds up large model inference, we're going to break down exactly how DeepSeek tackled this massive bottleneck right here, right now. All right, let's just kick things off with a staggering statistic. 60 to 85%. That is the per-user generation speedup DSpark achieves over the previous MTP1 baseline. And honestly, here's the absolute kicker. It does this with zero loss in output quality. We are talking about a completely lossless acceleration. This isn't a brand new standalone model, it's a brilliant optimization that simply reuses your existing weights to totally transform how fast you can generate text. So here's our roadmap for unpacking this incredible performance leap. We'll start with the need for speed, cover how speculative decoding actually works, dive into the DSpark solution, check out their smart hardware scheduling, look at the benchmark results, and finally wrap up with some real-world use cases. Let's get into it. Section 1, the need for speed. First up, we really have to address that universally understood bottleneck, waiting for an AI to actually generate text. It's a massive pain point, especially when you're dealing with heavy, concurrent traffic in a live production environment. At the very heart of AI latency, you basically only have 3 levers you can pull to speed things up. You can either draft tokens faster, verify them smarter, or draft them better so that more are accepted in a single go. What makes DSpark so unique is that it actually pulls all 3 of these levers at the exact same time to completely rewrite the speed limit. Section 2. How speculative decoding works. Let's look at how we conceptually fix this latency problem using a really fascinating technique called speculative decoding. You can think of this process kind of like a classic office dynamic. Imagine you have a super fast, maybe slightly junior assistant who quickly types up a draft document. Then you've got the slow, highly meticulous boss, that's your large target model, who reads and approves that entire block of text all at once. So instead of the boss writing every single word from scratch, they're just reviewing and correcting the assistant's quick work. In practice, this workflow happens in 3 specific steps. First, the small model drafts a block of tokens. Next, the large model verifies that entire block in just a single forward pass. And finally, a rejection sampling rule accepts the longest valid prefix from that draft and tacks on 1 bonus token. The crucial takeaway here is that this exact rejection sampling process preserves the target distribution perfectly, meaning absolutely zero quality loss in the final generated text. Section 3, the DSpark solution. Let's see how DeepSeek actually builds on this speculative foundation to create the ultimate optimized setup. Historically, engineers have kind of faced a classic Goldilocks scenario when choosing a drafter. On one side, you've got autoregressive drafters, like Eagle 3. They condition each token on the prior ones, giving you high acceptance, but man, their computational cost grows super heavy as the draft block gets larger. On the flip side, you have parallel drafters, like DoFlash. Now, they produce the whole block in one cheap pass, but because each position ignores its neighbors, they suffer from what's called multimodal collision. Basically, the tokens get confused and clash, leading to a really rapid acceptance decay toward the end of the sentence. So Eagle 3 is too heavy, DoFlash falls apart at the end, and that sets up the exact problem DSpark was built to solve. DSpark turns out to be just right because it relies on a highly clever hybrid approach. It uses a heavy parallel backbone for incredibly fast and accurate guesses on that very first token. But then, it introduces a lightweight predictor, specifically a sequential Markov head, to guide the rest of the draft and add bias based on what was just written. And since they compress this whole process using a low-rank 256 factorization, it stays incredibly cheap computationally. It holds the acceptance rate remarkably steady deep into the block, totally sidestepping that messy suffix decay we just talked about. Section 4, smart hardware scheduling. Because as it turns out, even with great drafting, verifying doomed tokens is just a waste of precious batch capacity on your servers. You see, raw neural network confidence is often, well, a bit overconfident. It thinks it's right when it's definitely not. To fix this, DSpark employs a specialized confidence head to score each draft position, accurately estimating the real chance that a token will actually survive verification. Then, it uses a post-hoc calibration step called sequential temperature scaling to dial down that raw neural overconfidence. This genius step slashes the expected calibration error from around 3 to 8% all the way down to approximately 1%. So now, the system precisely knows to only verify what is actually likely to pass. Armed with this incredibly accurate confidence data, DSpark then kicks in a load-aware prefix scheduler. Think of this as dynamic server balancing. When your GPUs are sitting idle, it aggressively verifies more tokens. But when those GPUs get busy and concurrency spikes, it dynamically trims the verification budget on the fly to protect your overall throughput. It perfectly balances the workload, and it uses an early stopping rule to guarantee the whole process stays strictly lossless. Section 5, the benchmark results. Let's put these 3 levers to the test and look at the hard data from offline tests across some different model sizes. The jump in performance is just undeniably clear here. DSpark beats both baseline drafters significantly when it comes to accepted length across QN3 models. We're looking at gains of up to 31% over Eagle 3 and up to 18% over DFlash. In fact, this architecture is so remarkably efficient that a tiny 2-layer DSpark setup actually outperforms a full 5-layer DFlash setup. That's a massive win. But what makes this performance even more impressive is the cost, or rather, the total lack of it. Scaling the draft length from 4 all the way up to 16 tokens adds a maximum of only 1.3% to the per-round latency. You are getting a huge boost in accepted length, up to 30%, for practically zero extra latency cost. It is an absolute triumph for efficiency. Section 6. Real-world use cases. Let's ground these theoretical benchmarks in reality for a second. Why does this actually matter for your specific workloads out in the wild? Well, different domains are seeing massive real-world improvements. For code generation, where token acceptance is naturally pretty high anyway, DSpark allows your coding agents to stream outputs much, much faster. In math reasoning tasks, those long step-by-step logic traces, the accepted length actually skyrocketed from 76.9% up to 92.5%. And for daily open-ended chat, a simple confidence threshold sweep raised acceptance from around 45% to a staggering 95.7%. Basically, DSpark's confidence head accurately flags those uncertain suffix tokens, pruning them early to dramatically improve real-world speed across the board. Honestly, the absolute best part about all of this is the accessibility. The DeepSeek research team has fully open-sourced the MIT-licensed DeepSpec codebase right along with the DSpark checkpoints. Because this is purely a serving optimization, you do not need to go and retrain your massive target model. You can literally just attach the draft module directly to your existing DeepSeek v4 weights right now. So we've seen how smart drafting, precise confidence scaling, and load-aware hardware scheduling all combine to completely rewrite the latency equation. As you consider the impact of reducing your inference bottlenecks by up to 85%, I want you to think about your own projects. How will this massive, completely lossless leap in speed transform your own AI development and the very limits of what you can build tomorrow?